Welcome and thank you for standing by. At this time, all attendees are in a listen-only mode. This webinar is being recorded and will be posted publicly. If you have any objections, you may disconnect at this time. I'd now like to turn the call over to Michael Hawes. Michael, you may begin.
Great, thank you. And thank you to everyone for joining us today for our webinar about the new 2020 Census Redistricting Data Noisy Measurement File. I'm Michael Hawes, and I'm joined by my colleague Matthew Spence, and we're going to kind of walk you through a little bit about what the Noisy Measurement File is, how you can access it, and how you can use it to perform some analyses on the 2020 Census Redistricting data. Before we jump in, I just want to invite you, if you have any questions, please submit them to us via the Q&A feature in the WebEx platform, and we'll try to answer those throughout the presentation. We're joined by our colleague Ryan Cummings-Menon, who's going to help us answer some of those, and then we'll have some time for additional Q&A at the end. Next slide, please. So before we jump into the noisy measurement file itself, it's helpful to understand a little bit about how disclosure avoidance for the 2020 census is actually being performed and how the noisy measurement file fits into that process. Disclosure avoidance for the 2020 census is a bit different than the disclosure avoidance we've used in prior decades. We've used noise injection for the decennial census since 1990. But for the 1990 through 2010 censuses, that noise injection was done in the form of swapping, where we would swap household records. Noise injection for the 2020 census is being applied through a framework known as differential privacy. And differential privacy really improves on those earlier methods by giving us an ability to really quantify privacy risk and privacy protection in ways that we couldn't do using more legacy methods. And it does this because, well, every individual that's reflected in any particular statistic contributes towards that statistic's value. Well, differential privacy as this kind of accounting framework for privacy risk allows us to kind of look at, okay, in each of those statistics, how much information about each individual is going to leak in the statistic that you want to publish. And by assessing kind of that individual's contribution to the statistic, you can then determine exactly how much noise you need to introduce into the statistic to control how much information about that individual will be revealed in the statistics that you're publishing. So it's a really helpful kind of framework for helping us really get a sense of how protected are the data that we are publishing. Next slide, please. Now, there's no one way to implement differential privacy. As I said, it's an accounting framework, not a method itself. So there's lots of different algorithms or approaches to algorithmic design that you can use within a differentially private framework. And for the 2020 census, we actually use different sets of algorithms to protect the different data products that comprise the whole suite of 2020 census data. Those algorithms are kind of broken down primarily into what we call the top-down algorithm, or TDA, and then SafeTab and PHSafe. Now, the top-down algorithm is going to be the focus of what we're talking about today, because that's the algorithm that was used to apply differentially private noise injection for the redistricting data, the demographic profile, and the demographic and housing characteristics file, or DHC. And the top-down algorithm essentially takes the confidential census data as its input, and it outputs privacy-protected microdata that can then feed into our traditional tabulation systems to produce the tables that that our data users rely upon. Next slide, please. So the top-down algorithm kind of works by kind of doing kind of at a high level a five-step approach. It starts by, as I said, inputting the confidential microdata, the census edited file. It converts these microdata records, these individual level records, into a functionally equivalent kind of histogram, which is a tabular representation of those microdata with counts of each possible combination of attributes or values that can occur. So it's the functional equivalent of microdata, but in a form that the algorithm can more easily work with. It then asks a series of queries or kind of tabulations off of those off of the confidential histogram, and injects noise into the results of each of those queries. So it might ask, how many people in this particular geography have this combination of characteristics? And then it'll take that number that it got off of the confidential data, and it'll add a very small amount of noise, maybe 0 or ±1 or ±2. But those noisy measurements are essentially the privacy protected answers to all of those queries that it asked off the confidential data. But those noisy measurements are often inconsistent with each other because we're asking all of these queries independently. So for example, if you asked a query, how many people live in a particular county, and then you separately asked how many males live in that county and how many females live in that county, you're getting 3 different noisy measurements with 3 independent sets of noise added to them. So if you sum the noisy count of males with the noisy count of females, that may not equal the noisy count of the total population for the county as a whole. So you've got these inconsistent, independent noisy measurements that you've taken. In order to kind of output microdata from the algorithm, we have to then post-process all of those noisy measurements to enforce internal and hierarchical consistency. So subcategories add to parent categories, and lower level geographies add up to their parent geographies. And so this post-processing step turns all of those independent noisy measurements into an internally and hierarchically consistent histogram, which we can then convert back into microdata for tabulation and publication. Next slide, please. So delving a little bit deeper, as I was saying, the noisy measurement step of the algorithm, in that step, the top-down algorithm takes a massive number of these noisy measurements of the confidential data, injects a small amount of noise into each of those results. But as I said, each of those noisy measurements provide different answers for the same question because the noise is injected independently. So the results differ from each other. We then post-process these noisy measurements into the internally and hierarchically consistent set of results. And in doing so, we also incorporate any corresponding invariants or constraints into the process. Now, invariants are data elements to which we add no noise. So things like the total population at the state level, or the total number of housing units at the block level, or the number of group quarters, of occupied group quarters facilities by major GQ type at the block level. Those data elements have no noise added to them. So we have to respect those numbers as invariant in all of that post-processing. The constraints are additional consistency and reasonableness rules that the post-processing has to impose as well. So things like you can't have a 5-year-old grandmother, for example. All of this post-processing within the TDA occurs, as the name suggests, in a top-down fashion, starting at the level of the entire US and then moving sequentially down each geographic level of the hierarchy until you get down to individual census blocks. At each level, the results and totals of the post-processing from the level above it are added to the constraints. So, for example, when processing the state level noisy measurements, the algorithm includes the already processed US level data as additional constraints in that post-processing process. Next slide, please. Okay, now the geographic hierarchy that the TDA uses differs from the traditional Census Bureau kind of standard tabulation hierarchy in a few important ways. The standard tabulation hierarchy goes like US to state to county to tract to block group to block. But as we were developing the TDA, we realized that in the context of producing the redistricting data, we discovered that overall accuracy of the data can be improved without any additional loss of privacy by modifying the hierarchy that the TDA uses to bring some important geographical entities that aren't on that kind of traditional tabulation hierarchy, bringing them kind of closer to the processing hierarchy that we use. So we did this for the redistricting data by separating out, for example, American Indian and Alaska Native tribal areas from the balance of their states. They got a separate branch of that processing hierarchy. We also reconfigured the top-down algorithm's definition of block groups to bring other geographies of interest like minor civil divisions, places, and individual American Indian, Alaska Native tribal areas closer to the spine as well. I do want to stress optimized block groups, these kind of reconfigured borders of the optimized block groups, are only used within the TDA itself. The tabulation block groups are used using the standard kind of tabulation block group definition. So any published tables in the official redistricting data file, for example, use the traditional block group boundaries. Within the TDA and within the noisy measurement file, you'll see these optimized block groups that have boundaries that differ. And we'll talk more about that later as we delve into the noisy measurement file itself. Next slide, please. Now, I do also want to stress, so this noisy measurement stage of the TDA asks that series of queries off of the confidential data, adding noise to all of those results. The set of queries isn't like there's no one set of queries you could use. You can ask any number of different queries to achieve the overall result. What you see on the screen here is the set of queries that we discovered in our experimental runs on the algorithm, yielded the most accurate and usable redistricting data at the end of the process. So we have this series of queries: total population, race, Hispanic origin, voting age, not voting age, etc., and then crosses of those, where we're then asking those queries of the confidential data at different levels of the geographic hierarchy. So we'll ask query at the US level, then at the state level, at the county level, and so on. Each of those queries receives an allocation of the overall privacy loss budget. The privacy loss budget is what determines how much noise gets added into each of those noisy measurements. So what you can see here are the allocations of privacy loss budget that were applied to each of those queries at each level of the geographic hierarchy. The higher the privacy loss budget, the more accurate the resulting statistic will be, because there's less noise getting added. The lower the privacy loss budget, the lower the share, the more noise that gets added and the more protected the data are as a result. Next slide, please. So used a bunch of different terms here. Let me kind of delve just a little bit deeper so you understand the terminology when we're talking about different types of files here. So we've got noisy measurement files, we've got privacy protected microdata files, and we've got published tabulations. This here on this screen is a kind of visual representation of how the algorithm kind of goes through its sequence. It starts with the census edited file. It takes a series of queries, adding noise to the results of those queries, giving you the noisy measurement file, which are privacy protected tabulations without enforced consistency between them. Then those noisy measurements, the noisy measurement file, is post-processed through those sets of invariants and constraints into privacy protected microdata. Internally to the census, we call that the microdata detail file. Externally, we call that the privacy protected microdata file. That is essentially an individual level record for every person in the census that then gets tabulated into the published redistricting tabulations that formed the 2020 census redistricting data summary file. So you've got kind of the CEF to the noisy measurement file, through post-processing to the privacy protected microdata, which are then added up to become the published tabulations. Next slide, please. So should you use the noisy measurement file? Should you use the PBMF, or should you use the published tabulations? Well, the answer to that question is going to depend on what you're interested in doing with the data. And in order to understand that, you have to recognize that there are going to be two sources of disclosure avoidance related error in the published statistics, the tabulations or the PPMF. You've got the differentially private noise. That's the noise that we have to add in order to protect privacy. And then there's post-processing noise. That's the noise that results, or error that results as a function of kind of enforcing consistency between all of the data points. Now, the differentially private noise is unbiased. It behaves according to a known distribution determined by the amount of privacy loss budget that was assigned to a particular query at a particular level of geography. And so that differentially private noise is the only disclosure avoidance noise that you will see in the noisy measurement file. Now, the error that results from post-processing is data dependent. because we have non-negativity requirements in order to make sure that you don't result with a negative count of people in a particular geography. That non-negativity requirement means that there's going to be a small amount of positive bias in some small counts in the resulting data. And because everything has to add up to state population counts, then that means that that small positive bias in small counts has to be offset with a small negative bias in large counts. The top-down algorithm also reduces the amount of error for many statistics relative to their corresponding noisy measurements. Because we're constraining at each level to the results from the higher level, block-level statistics produced and protected by the TDA will often have much lower variation, much lower overall error than you would expect solely based on the amount of privacy loss budget that was assigned to that particular query at the block level. So what you've got is kind of introduction of a little bit of bias through post-processing, but much greater accuracy as a result. The noisy measurements don't have any of that bias. They are unbiased because all of the noise is done independently, but they will be slightly less accurate than the post-processed data that you see in the PPMF or the published tabulations. Next slide, please. So, kind of answering the question, should you use the noisy measurement file, should you use the PPMF, or should you use the tabulations? Well, I want to stress the 2020 Census Redistricting Data Summary file and the 2020 Census Demographic and Housing Characteristics file include the tabulations that are processed through the entire TDA. Those represent the official 2020 census statistics. As I mentioned, they have higher accuracy because of the nature of the post-processing that occurs in that top-down fashion. But that post-processing and that higher degree of accuracy does introduce small amounts of bias because of how that post-processing takes place. The 2020 Census PPMF, the privacy protected microdata file, is a 100% microdata file that is fully consistent with all of the published tabulations in the redistricting and DHC files. The 2020 Census PPMF will be very useful for people who want to do special tabulations, for example, or who want to do microdata analysis on the privacy protected data. The 2020 Census Noisy Measurement Files, the redistricting noisy measurement file that we're going to be discussing today, and the Demographic and Housing Characteristics noisy measurement file that will be released later this year, those noisy measurement files can be used to produce unbiased estimates and confidence intervals from the 2020 census. These can also be used to evaluate alternate post-processing mechanisms. TDA is just one way of post-processing the data. So we welcome researchers to look at, okay, from those same noisy measurements, how could they have been post-processed different? Identifying ways of maybe improving upon what we did. And so these are a research project. These are a research-based statistical product of the census in contrast with kind of the official core statistics that form the official 2020 census data products. Next slide, please. And with that, I will turn things over to my colleague, Matt Spence, to walk through how to find the noisy measurement file and how you can use it to generate some estimates and confidence intervals.
Thank you, Michael. Really great background information that we will be drawing on for our section, for my section of the presentation as well. So very good, very exciting news. We've released the 2020 Redistricting Noisy Measurements files supporting metadata and documentation at both the ICPSR at this link here, as well as the Harvard Dataverse, which is at this link here. So we've got sort of pictures of both websites. Previously, we had released the 2010 redistricting data via the ICPSR. So this is exciting to be able to have them at both places. And so here is an example at the ICPSR at the University of Michigan. This is the 2020 redistricting data file, noisy measurement file. If you are interested, you can read about what this file is about. You can see that we have links to our production code and a little bit more information about sort of how to view it and how to see it. The one thing I will say is if you're using the ICPSR, you have to download a special software called Globus which will allow you to access the data, and that is not allowed on our Census work laptops. So I will not be showing you that. Instead, I will just be walking through an example here. You can see here that you'll need to register with a Globus ID if you're using, again, if you're using ICPSR. And then you can sign in. And then once you're there in the Globus software, you'll be able to access the different sets of files. This is the DDPS. You know, this is the 2010 Redistricting Noisy Measurements file. So the DDPS is the Demonstration Data Product Suite, which we released back in April. That contains 2010 data that's gone through the production software with the production settings and the production parameters, the same settings, the same parameters, the same software as 2020, but on 2010 data, so that people can then take that and evaluate it. It's demonstration data, so data users can evaluate the fitness for use by comparing the 2010 data to what was published and protected using the traditional swapping method. So this is what I'll say about the ICPSR is, that Globus is available there, and there's a great tour if you need help with the software. For the 2020 version, it's also available on the Harvard Dataverse. The nice thing about the Harvard Dataverse is that you can easily just download the well, you used to be able to download the 15 gigabyte file. It's apparently not available anymore. But you can also go down, and most people are not going to want to download 15 gigabytes in a zip file. So you can preview the zip file, which is very nice. And you just, put in your name, your email address, put in a little bit about what you're going to use the data for. Hopefully you're a little bit less brief than I am. And you hit accept, and then you'll be able to browse the 4 different. Oh, great. Thank you, Michael, for clarifying. The 2010 redistricting NMF is also now available on the Harvard Dataverse as well. So the nice thing about this is you don't need the Globus software, so anyone can view it. I see there's a question in the chat, Michael, if you can address that. So if you can't access the data in Globus using ICPSR, perhaps the Dataverse at Harvard is a better option. So as I said, there are 4 different kinds of file. There's a separate file for Puerto Rico that have persons. There's Puerto Rico units file, and then there's US, including DC person file and US unit file. So what do we mean by person and unit? Traditionally, Census has gathered data both about individuals and the individuals grouped into households or group quarters, things like that. And so that if there are statistics on families, households, tenure, all of that would be in the unit file, because those are sort of individuals grouped together. If there are data that you're interested in that are things like individual person ages, individual sex, or even relationships to the householder, you can find that in the person file. So let's just look at the person file. We have split these into different geo levels, and you'll see this this file extension is called Parquet. It's not the floor, it's not the butter substitute. It's a file type that allows storing very large data in a very efficient format. Thankfully, many modern statistical packages can read Parquet files directly. But if not, we have some sample code that will allow you to read the Parquet file and save it into like a CSV, a comma separated value file, or a text file that you could then pick up with a different software program. So each geo level is broken up here. You can see here's the US. So this is where you would get estimates for the entire US. State, so you'd get estimates for different states. County, tract, block group, and block. So let's open up state. Now there are two different folders within each one of these. There's the constraint file, and then there's the DP query. The constraint file is what Michael was talking about earlier, where we learned about different constraints, such as no 5-year-olds being allowed to have a relationship to householder of grandmother. There are other constraints, that exist and are summarized in these constraint files very nicely. And then the DP query is actually where the noisy measurement data live. These are where these noisy measurement files exist. Now there are a couple of things to note. One is you can see immediately state equals 141. Which state is 141? I thought there were only 50 nifty United States. Well, this is because the first digit here refers to whether the state is a non-AIAN state or the AIAN part of state. So certain states have American Indian, Alaska Native, or Native Hawaiian homelands. And those states end up having two different entries, one that starts with a 0 and one that starts with a 1. Other states that have no American Indian, Alaska Native, or Native Hawaiian homelands are not split up in that way and only get a 0 in front of them. So you can see here, this is state 41, which I think is Rhode Island, that is the AIAN part of it. And then lower down, I should have found it earlier, but I can't. Here it is. Here's 41. That's the non-AIAN part of it. So again, these decisions and what Michael was covering earlier about the way that the geographic spine was manipulated in order to produce more accurate estimates has impacts on how these noisy measurements are displayed and how they're useful. The same organizational practices apply to the unit files and, of course, to Puerto Rico as well. Although there's no US level, there's no national level for Puerto Rico. But in general, it's the same. So going back to my slides. So this slide covers what we were just talking about. You remember how the states, a state could appear in two places. It could be 141 and 041. Well, that also applies to all of the geocodes within the noisy measurement file, within these different parts of the noisy measurements. So you'll see that the Bullock County, Alabama, has a DAS geocode of 0, which indicates the non-AIAN NH spine. 01, which is the FIPS code of the state, Alabama. 10, which is filler digits for all DAS geocodes. And then 011, 011 for the FIPS code for Bullock County. So that is pretty straightforward for states, and it's pretty straightforward for counties. But when you get down to tract and block group levels, because of the way the optimized block groups were formed, that's where we really need to not just sort of come up with this, relying on the FIPS codes. We really need to look at a block level crosswalk between the tabulation block geocode and the DAS block geocode. So we've got an example here of Bourbon Street, New Orleans, Louisiana, because we presented this research initially at the Population Association of America in New Orleans back in April. So that's why we're spotlighting this particular block. But you can see that some of these numbers look very similar. 22 for Louisiana, 071 for the county. And you can see 22 is over here, and it's the non-AIN part of it because it starts with a 0. There's that 10 that was inserted in there as filler. And then there's 071, which matches the 071 in the tabulation geocode. And then the rest doesn't really match up. You can see that in the tabulation, it's tracked 135003. That is not how it's represented here, because again, it's gone through this optimized block group reshuffling in order to find the best place for these crosswalks. We recommend that you go back to the original file, you go to block, and then you look at the actual constraints, and the constraints will have all of these geocodes put together. So that will allow you to reformat the sort of crosswalk between the tabulation block geocode and the DAS block geocode. The final 16 digits of the block geocode are always what was tabulated. So as we discussed the structure of the component files, separate person and unit runs for the US and Puerto Rico, subdivided by geographic level. Within each geographic level, we're divided into DP queries, which are the actual noisy measurements, and constraints, which discuss sort of what constraints, what equalities are held or what inequalities are held. And we discussed how different states will have, an AIN portion and a non-AIN portion. So there'll be two different folders for states with AIN NH areas. And then all of the Parquet files start with PART because they're parts of the whole. And then they have a very long random assortment of numbers and letters that will be unique. So you can uniquely identify this is the block constraint for the AIN portion of Rhode Island, using this SNAPPy Parquet. SNAPPy is the compression algorithm that is used for these particular files. So let's get into it. Let's see what we're talking about. Actually, before we do that, I'm sorry. I mentioned that many modern statistical packages can, in fact, directly read Parquet files. We encourage data users to use these statistical packages. Even statistical packages like Stata and SAS may have add-ons that allow you to directly access them. Otherwise, if you're not able to do that, we recommend using either Python or R to use code similar to this to read in the Parquet and output a CSV file that then you can pick up in others locations. There is one challenge with that I will mention in a second. So let's look at what these data look like. So, I'm switching now to sort of a live view. I'm using Python here. I'm going to read in a county file, which is here. This is in the Alabama county geo-level part. And this is the tract for Alabama part file. I will note that this is using 2010 data because when we were creating these slides, 2010 data were what were available, but this is a very similar process that you can use to look at 2020 data as well. So let's first look at that county that we discussed earlier, Bullock County. So we said, okay, let's look at the non-AIN portion. So that's 0. 01 is the FIPS code for Alabama. 10 is the filler digits. And then 011, that's Bullock County. And so we can see, this is what the noisy measurements actually look like. You can see there are different rows for different measurements. There's one for total, which is the total population. There's one for Sen race, Hispanic origin, voting age, HH institutional levels. So those are whether you're in an institutional GQ facility or not, or in a household. HHGQ, which is a little bit more information about major types of GQ or household. And then some cross tabulations as well. So this is Hispanic multiplied by CEN-RACE. So, for example, non-Hispanic white, Hispanic white, non-Hispanic black alone, Hispanic black alone, etc., all the way to Hispanic 6 races, and then not Hispanic 6 races. Then we also have voting age by CEN-RACE, etc. And you can see that some of these start to get very detailed until we get to the detailed query, which is all of the different characteristics sort of crossed by one another. So that's what the query name means. We also have a couple of helper variables here that mention about whether what the cross tabulation is about. You can see for total, all of them are star, so that doesn't really, there's nothing really being cross tabulated here. But for CEN-RACE, you can see there's CEN-RACE. And for Hispanic, there's Hispanic, voting age. And then you can see that for these cross tabulations, it's Hispanic and CEN-RACE showing up in the sort of helper indicator variables. Next, we have something called a query shape. So this is where the tab, converting it to a CSV, it's a little bit problematic because sometimes if you convert to a CSV, it's difficult to pull out. These are essentially lists in Python or vectors in R. They are, a group of variables, a group of values meant to stay together. And so, pulling it out to a CSV doesn't always sort of make sense in that case. So that's why it's better to directly manipulate the Parquet files if you can. So this is just telling you that it's just a there's really just one value. And you can see that because the value is 10,911. We also have the variance, which is 4.701627. And we also have a representation of how much privacy loss budget was put at this particular level for this particular query. And it's represented as a fraction. So this is the first number is the numerator, the second number is the denominator. So total is pretty easy because it's just one. But what if we were looking at CEN-RACE? Well, you can see it's 63 long. So it ends up being 63, it's a list with 63 different elements. So you can see it's 2,463 for CEN-RACE 01. CEN-RACE 02 is 7,606. Then we have 83 for CEN-RACE of 03, minus 12 for CEN-RACE of 04, etc. So that's right. So there are negative values in these noisy measurements. And as we'll see in a bit, it's important not to disregard those. We can see here now that the variance is much greater. It's now 1,469 instead of 4.7. And that reflects what Michael showed earlier, that, and it's also reflected here in the PLB, that this particular query for this particular geography level did not get a very large amount of privacy loss budget. Now, again, I'm just going to stop and say that doesn't mean that the final tabulated results will be off by this much, right? This is just a representation of where we are in that intermediate step for these noisy measurements before the post-processing takes hold. The post-processing will greatly increase the accuracy, even for queries like this one, which didn't get a lot of privacy loss budget applied to it directly.
And Matt, I'll add to what you were saying.
Yeah, please.
There. And we're also, if you look at the full list of queries, you'll see that that's just one query that includes CEN-RACE. There's a bunch of the others, including cross tabulations, that also include CEN-RACE, and all of that information gets combined together in the post-processing.
Yes, that is a really good point. Yeah, so this is just directly measuring CEN-RACE, but the really interesting thing about these noisy measurement files and the post-processing that we're actually going to demonstrate in just a second is that the post-processing takes the CEN-RACE values from the direct measurement, but it also takes the CEN-RACE values from this cross-tabulation and this cross-tabulation and this cross-tabulation and the detailed query, and it puts it all together. And by bringing all of these in, all of these different variances in and different estimates in, it can get a much more precise margin of error. You can get a much more precise confidence interval from that. Okay, So let's go back to our PowerPoint slide. So we've seen what this looks like. This is another way to look at it. This is sort of using a slightly different software program to view it. So let's look at doing a confidence interval. Now I have a separate document here, which our colleague here, Ryan, did a lot to write for, if not most of it. So thank you to Ryan for all of these great examples. But I'm going to walk through them to the best of my ability. So there's a lot of information about these different noisy measurements, sort of about what they mean. We also set up a few helper functions here in Python to create different distributions, uniform distribution, Bernoulli, etc. And the fun one that we like is discrete Gaussian. That is the one that we typically use here as part of our work. So I'm going to scroll down, and we have a couple other sort of helper parameters here as well. Okay, so example 1, generating the confidence interval for the estimate of the total population of Bullock County, Alabama, which has an internal DAS geocode given by, everyone know, together, 0, 0, 1, 10, 0, 11. We've seen this again and again. It's our favorite example. So based only on the total population query primitive DP answer. So that's a really interesting sort of caveat. And that goes to what Michael was saying earlier, is that the true top-down algorithm post-processing and any other post-processing that we would consider would in fact take information from many of the different noisy measurement files to get a much more accurate range. And that in this example here is just taking one query. So, all right. So we're going to just use a sort of an approximation here for this particular example. You can see here that this is only looking for a different across 1,000 different simulations. This is not the most accurate. We'll use more accurate methods in a bit, but this is just a kind of quick approximation, because we know that you can, for any particular noisy measurement, for any one noisy measurement, you can use just a normal distribution and the share of the privacy loss budget allocated to that measurement's query to get a really nice approximation. But if you use a simulated discrete Gaussian distribution that we will later, you'll get a more exact confidence interval. So what we do is, we just kind of go back to that noisy measurement file. So we say, okay, we're looking at total, again, for our geocode. And we know the value is 10,911. So that gets plugged in as the answer. And then we know the variance that comes from the variance parameter here. That gets plugged in. And then this is our sort of, again, approximation, our quick approximation technique. And we can see that the confidence interval for the total population for Bullock County is the noisy measurement, 10,911, plus or minus 4. Plus or minus 4. But again, we know that that is throwing away a lot of other information that we could potentially use. So can we get better? Can we do better than plus or minus 4? Well, let's see. So example 2 is one example of how the post-processing system uses multiple noisy measurement queries and values to come up with a more precise estimate. So could we obtain a tighter confidence interval by incorporating the child-tracked total populations of those? So we can do a very similar process, and this, this paragraph here discusses a lot about this, but we're going to sort of scroll down to the payoff, which is to say, once you set up the coefficient matrix in the way that's described above, in order to account for the various geo levels that are being brought in here, then we're bringing in the county number. So this is the variance of the county, which is what we saw right here. The variance of the tracts, so I'm going to scroll down to the next. These are the tract level geocodes, only looking at the total query. So you can see here that the variance for each one of these is the same, which makes sense because we don't distinguish between different geo units of the same geo level. They all tend to get very similar allocations. So the variance is the same, 6.110105. So that gets plugged in here. And then the DP answers represent what the actual noisy measurement values are. So we remember 10,911 from before. Now we also have 1,433 for this tract, 7,105 for tract 2, and 2,376 for tract 3. And we see those here. And then it runs through this simulation-based confidence interval approach with these parameters here, and we can get a much better estimate. We've shaved it down by 0.8%. That's great. So we can see again, so now it's not exactly 10,911 on the dot. We can see that it's actually slightly higher than that. And that's because, again, we took information from the child tracts and we gathered that along with the county's direct estimate noisy measurement, the value for the county. So that has changed slightly. But also we see that the confidence interval is narrower. Now we're at 3.2 or so. So we've been able to decrease the width of that confidence interval relative to the first one. So this leads to tip number 2, which is even when you measure the statistic of interest in the noisy measurement files, you should also see if you can incorporate additional information, for example, for child geo units, in order to obtain more precise estimates. This is what Michael was saying earlier, where we were talking about CenRace. If you just look at CenRace, that's one thing, but if you can bring in all of the other queries that also reference CenRace, you'll be able to get more precise estimates and smaller confidence intervals. So we're going to do a couple of additional examples here. One is, as we discussed, there are states where there are AIAN-NH area portions, and states where there are and those states also have non-AIAN-NH portions. Other states with no divide are just represented once. So Menominee County in Wisconsin actually is split. It has part of it is in the AIAN-NH geo unit, and part of it is not in that split. And again, we've learned that through looking at the block geocode crosswalk, which is in the constraint file of the block geo level unit. So we've sort of given the answers here a little bit for ourselves, that here are the DAS geocodes for these units. Once again, you can see 0 is the non-AIAN part, 55 is Wisconsin, 10 again as filler, and then 078 as the county. And then it's the same geo unit geocode except for the one preceding it, which represents the AIAN part. So let's go ahead and estimate the total population for the county using the 2 constituent parts. We put in the variance of the county. That enters in twice because, again, there are 2 parts of it. And these are the 2 individual, one is the AIAN part, one is the non-AIAN part. Once again, we do the simulation-based confidence interval estimation, and we're able to get the total plus or minus 5. So here's again, looking at the total within 5. So that's, even though we're combining 2 different estimates, each with their own variance of 4.7, we're able to get that confidence interval about plus or minus 5. Okay. So remember, tip 3, always take a look at that block crosswalk to see if individual geo units are split into AIAN and non-AIAN portions. Next, let's move south to Redfield, Iowa. Okay, So Redfield, Iowa is an interesting place. It actually is composed of 2 different optimized block group GeoUnits. So these, you can see, they have very, very different numbers here. It's not like before where we're seeing, they're 104 and 103, even though you'd think, okay, they may not necessarily have that. They certainly don't have that representation in the tabulated block group. So again, always look at that block crosswalk to be able to see the 2 different values here. Okay, so we were able to pull these 2 internal DAS geocodes. We're once again interesting at looking at the total population primitive DP answers to compute this estimate. So here we've got the variance of the optimized block groups is 3.069, and the 2 different parts of it are 696 and 139. We do the exact same, simulation-based confidence interval estimation, and we can get a total of 835 persons, plus or minus 4 persons. So that leads to tip number 4, which is when you're generating estimates and confidence intervals for custom geographies, it's better to minimize the number of operations you do. So for example, if you have a school district that's made up of 3 different tracks plus 1 block, it's best to add up those 3 tracks plus 1 block rather than individual blocks, however many, tens of blocks. And again, that comes in because the number of different levels being aggregated directly comes into this sigma squared parameter here, and that will greatly impact the amount of how wide these confidence intervals are. So in general, it's going to be better to do fewer operations rather than sum up individual blocks, for example. So let's go back to Bullock County, Alabama. This is our favorite example here. So let's look at what is the confidence interval for the total population when we look at both total population and voting age. Now remember, we talked, Michael mentioned that when we were looking at CenRace, you don't just look at the CenRace directly. You also include how CenRace is broken, is cross-tabulated by Hispanic origin, cross-tabulated by voting age, and all of these other different queries, including the detail query. Here, we're trying to get a slightly better estimate. Remember how we earlier looked at the child GeoUnits? We looked at the 3 different tracks that are part of Bullock County. Now we're going to try to look and say, okay, staying within Bullock County, not looking at the tracks, but staying within Bullock County, let's look at the total, and then let's look at the 18 and over population plus the under 18 population as a measurement of total population as well. So that's what we're doing here. It's very similar to the example that we did above, where we said, okay, what's the county's total population in the 3 tracks? But we're instead now looking at different queries for the same GeoUnit. And we can kind of go back to our favorite example here. And now we're looking at the total DPQ and the voting age DPQ. So we can see here, again, it's that 10,911 with that variance that we expected. And for voting age, it is 2,481 people who are under 18 and 8,435 people who are 18 and over. Those are the noisy measurements values, and then the expected variance here. So we go back in. So the total population variance comes in at 4.7. The voting age variance comes in around 1,469 or so. Those sigma squareds come in like this, where the total population is added once, and then the variance for the voting age gets added twice, because again, the under 18 and then 18 and over. So this ends up creating an array that's 3 long. And then the answers, we have the 10,911, the 2,481 who are under 18, and the 8,435 who are 18 and over. We run it through the machine, and we get the answer, which is our confidence interval right on, very close to the direct estimate for total population, 10,911. But you can see that the confidence interval is actually a little bit wider. It's 3.86, whereas before, in example 2, it was 3.19. So we've lost, relative to including the child unit tracked total populations, we've lost ground a little bit from that. And so that's a little bit odd. And so we think, well, why would that be? Why is that wider? And the answer is it's all about how much privacy loss budget has gotten allocated to these different parameters, these different queries, and these different geo levels. Total population at the county level got a lot of privacy loss budget relative to other queries and geo units. Tracked total population also got a lot of privacy loss budget. So those will end up, being, somewhat more accurate, and using those answers will be better. And you can see that again by looking at the variances. Remember, the county total population variance was 4.7, and the tracked variance was 6.1, versus in example 5, the voting age variance is 1,469. So that's a much wider variance, indicating a much smaller amount of privacy loss budget was put on that query. So it doesn't really help you that much. You're helped relative to example 1. Example 1, which was just the direct measurement of total population using only total population, that was plus or minus 4. So we do see that bringing in voting age decreased 4 to 3.86, but bringing in tracked total population would decrease it even more to 3.1 or 3.2. So noisy measurements with larger PLB allocations will generally produce more precise estimates with narrower confidence intervals. So try to choose the ones with the larger PLB allocations. Okay, well now, guess what? We're doing it. We're doing both. We're combining both example 5 and example 2. We're going to say, let's grab the total population and the voting age for Bullock County, Alabama, and its 3 child tracks to attain the tighter confidence interval. So what do? Again, we create the matrix based on the instructions above for how, we're bringing in all of these different units. Where the variance for the total for county is that 4.7 number. The voting age variance for the county is 1,469. The total pop variance is 6.11. And the voting age tracked variance is 1,914. And then, so all of those get combined into, we've got county, we've got tracked, and then we've concatenated those into the sigma squareds. And then the DP answers are this array. So again, here's the total population directly measured at the county. Here's voting age at the county under 18. I'm sorry, under 18 at the county based on the voting age query, 18 and over at the county based on the voting query, and then the individual numbers for the tracks and the voting ages for the tracks. And we run it through the machine, and what do we get? We get a very similar point estimate, 10,911, once again. And we can see that, it's actually 3.21. It's not quite as narrow as example 2. That does seem a little bit odd, but our guess is that this may be just due to the fact that we didn't use enough simulations in this example. We only used 10,000 simulation iterations. So perhaps doing 1 million might be able to suss out that exact added accuracy, because again, we are combining total population and voting age at the county level, and then information from each of the constituent tracks as well. So what do we learn? Incorporating additional noisy measurements with small PLBs might help the estimate and the confidence intervals, but the improvements might be minor. Maybe minor. Okay, now here's a fun one. All right, so we're going to now look at the HHGQ primitive. So going back to our example here, once again, this is DFC, so this is the county. We're looking at the HHGQ metric, the query, I should say, for this particular county. Once again, we're trying to estimate the total population of Bullock County, Alabama, and we're going to use HHGQ to try to inform us of that, because these are mutually exclusive categories. You're either in a household or you're in a GQ, and if you're in a GQ, you're in one of the major types of GQ. So we create our variance of the county. This variance comes from the variance here for this particular query, because we're only using this query. And then we bring in the individual DP answers, which are the same as these here. Now note that a couple of these values are negative. And we will absolutely want to include those negative numbers. That is something that we need to deal with when we're working with the noisy measurement file. We'll run it through the simulation-based confidence interval approximation, and we're left with not a great estimate. We see that now the estimate is 10,940 instead of 10,911, and we see that the confidence interval is plus or minus 205. And so the point of this one is that we have ignored more directly relevant noisy measurements. We've ignored total. We've even ignored voting age and the other ones, and we're trying to sum up from HHGQ. So that's one of the reasons why it's sort of a cautionary tale of, when you're choosing what to pick from these noisy measurement files, try to pick the ones that most directly measure your quantities of interest. Additionally, don't sleep on the negative numbers. Do not leave them out. If you had suppressed these negative numbers, the actual count would have been much higher. It would have been 11,027. So that would have been even further off than the 10,940 was. It would have resulted in a substantially greater error, because again, the published count was 10,914. So don't ignore noisy measurements. The inclusion of these noisy measurements can increase the precision of the estimates. It can sort of help deflate artificially inflated ones, and be mindful of how you construct these estimates. The detailed query might be what you think of. You might think, well, I'm just going to go to the detailed query and I'm going to sum up, as I need to, the different levels. But because the detailed query has a fairly low share of privacy loss budget for each item, for each part of the query, it would be less precise than using more focused noisy measurements. Let me go back to my slides, and the slides walk through these examples, and I believe these slides will be available. The slides walk through this discussion, exactly what I was just covering, and includes all of the tips as well. So where are we at the end of the day? We've got 3 different estimates for 2010 number for each of these areas. Again, we've got Bullock County, Alabama, which we've been looking at. We've got Menominee County in Wisconsin, and we've got Redfield, Iowa, which is a place, not a county. So the published SF1 data in 2010 was 10,914. Now that does include swamping, but
actually it doesn't, because these are total population counts.
That's right. I'm so sorry. Yep, that's right.
That's why we use the total population.
That's right.
Because it would allow us to actually show the.
I said it, and it didn't sound right when I said it. So I said, okay, I better pause. So thank you, Michael. Yes. So yes, the 10,914. So we can kind of treat that as a ground truth or an enumerated truth for 2010. The 2010 privacy protected microdata file, which is also what was published in the redistricting tabulations, which is also what was published in the DHC tabulations. for these demonstration data products was 10,912. Again, this is 2010 data that's been run through the 2020 software with production settings and production parameters. So it's very, very close. It's within 2. And then looking at the noisy measurements file, you can see the confidence interval here. It's 10,911.61 plus or minus about 3.2. Plus or minus 3.2. And you can see that that value, that confidence interval encompasses the SF1 value for that. So you end up getting fairly close with the noisy measurement value once you've taken into account the different ways of bringing in, like if you can bring in the child tracts, for example. Menominee, Wisconsin, slightly wider confidence interval, plus or minus 5, and that's again because we had to estimate it by taking in the AIAN portion and the non-AIAN portion of the county. But still, all that said, the point estimate is exactly what the SF1 demonstrated. It's 4,232, and the demonstration data product suite, PPMF, was 4,230. So after the top-down algorithm, it got slightly further away than what the noisy measurement file demonstrated, but it's still rather close. And then lastly, Redfield, Iowa, which, as you'll remember, we combined 2 different optimized block groups to form Redfield, Iowa. All 3 estimates are spot on the same, 835, and the noisy measurement gives a nice example of plus or minus 4. So, again, bringing in those 2 estimates means it's slightly wider than you might expect, but still plus or minus 4 at 835. And just for comparison, we've pasted in 2 tables that show simulated error in households for counties to demonstrate sort of what kind of variability we can expect from non-sampling variability, coverage errors, imputation errors, and the like. We're working on additional guidance that will sort of summarize a total uncertainty framework for the decennial census. We're not ready to discuss any of our results just yet, but we are working on that research in order to really kind of nail down just how fit for use are the data for your particular purpose. So with that,
I'll kind of add, so the reason we included these here is to kind of give a sense of, okay, so we're seeing from these noisy measurements compared to the original published SF1, again using the 2010 data, we're seeing kind of what the confidence intervals tend to be like at the county or place levels, and then if you compare that, you can to the 2 tables that are pasted below there, you'll see that magnitude-wise, the magnitude of disclosure avoidance error in these cases is dwarfed by the size of the kind of operational and coverage errors that we know occur in the census. So you can see the magnitude is much smaller.
Great. With that, we'd like to open the floor for discussions or questions. I don't see. Oh, I do see there are a couple of.
Yeah, we've been answering a lot of the questions.
Okay, great.
We've been answering a lot of the questions as they've been coming in. Please, if you have questions, put those into the chat and we will read them out and answer them now. I will also say, so since we released the 2010 redistricting noisy measurement file back in early April, we have seen some scholars and data scientists and statisticians digging through it and working with these files, and we've kind of started to see some results from those analyses. We've also started to see some challenges that people have had working with these files. So I will kind of, while we're waiting for some more questions to come in, I'll kind of highlight 2 words of wisdom or pieces of wisdom that we've learned based on people's uses of the data so far. The first is always, and this was included as one of the tips that Matt read, always double check if there is a corresponding geo unit. If you're interested in a particular geo unit, always check on both the AIAN portion of the spine and the non-AIAN portion of the spine, because you may need to be combining those two different sets of noisy measurements to get accurate information for a particular geography. So that's piece of advice number one. Piece of advice number two is, depending on what geo units you're looking at what levels of geography, you may think that some of the noisy measurements are missing. You may be looking for a particular block, for example, and you go into the block level data and you don't see that block there. That is a function of the spine optimization that we talked about briefly before. In cases where a parent geography only has one child geographic unit under it, for example, a tract that only has one block group, or a block group that only has one block, the optimization that the DAS does takes all of the privacy loss budget that would have been expended at the block level or at the child geographic unit level and reallocates it to the parent level and takes all the noisy measurements at the parent geo unit level. So if, for example, you go in and you're missing a block in the files, those noisy measurements will be included in the level above it because of that spine optimization. If you need to find out kind of where this is occurring, if this is kind of not showing up, that's where the kind of crosswalk that's in the constraints file with the dash geocodes can be helpful, because then you can find, okay, what's the geocode for the parent that you need to look at. So that's the kind of two pieces of wisdom that we've gotten from external data users kind of work with the noisy measurement files so far. Okay, I'm looking to see if any more questions have come in.
I'm seeing a couple of questions about the geocode crosswalk. I'm wondering if Ryan would be so kind as to come on and chat about that.
Hi there. Yeah, sure, I'd be happy to. So the question is, I'll just say it verbally here. I'm not sure, I don't think everyone has access to it. But the question is that the README file indicates that the block level geocode is 31 characters wide, but it doesn't tell me what each position in those 31 characters represent. So this question is from David Van Ripper. So the README file says exactly what you said, that the block geocode length is 31 characters. It also says that the optimized block group width is 15 characters. So those first 15 characters of the block geocode would represent the parent optimized block group geocode. So that's how we encode a hierarchical spine using geocodes, is we, the first few digits, so in this case 15 digits, represent the parent geocode.
Seeing if I can pull up.
Actually, I pulled it up for you here.
Oh, great. Okay, thank you.
You can say like each of the levels and the respective geocode widths for those levels. So yeah, it does go through. So you've got the 2-digit state code, the 3-digit county code, 6-digit tract code, etc. Any other questions here? Oh,
looks like Jay June has a question.
Jay June, Yeah, so more about the total error framing. This is research that's still in the early stages. It's something that we've known. So we measure after each census, we assess the kind of the different known sources of error in each statistic, whether it's coverage error, operational error, et cetera. Historically, we've never been able to incorporate disclosure avoidance error into those kind of public statements, but it's something that we are interested in doing. So it is something where we're looking to see, are there ways that we can kind of estimate when you factor in all of these different known sources of error, what can we say about kind of the resulting accuracy and fitness for use of the data with all of these known sources of error incorporated. So that is ongoing research. We don't have an estimate of when it will be done, but stay tuned and we'll let you know. All right, well, I am not seeing any more questions coming in. Last chance for a question, if anybody has one. All right, well, in that case, thank you all for joining us today. I'll turn things back over to Greg to close us out.
Thanks, Michael. Thanks, Matthew. And this concludes today's webinar. Thank you for your participation. You may disconnect at this time.